Okay, so let's keep cooking. I don't think we had any homework for today. Last time we were talking about, oh, wrong slides. I'm writing a casino simulator for loyalty programs on cruise ships. So I implemented a slot machine that has roughly the hit that a slot machine has on a cruise ship. And then I'm running it 5 million times to create strategies for hitting loyalty points to get free cruises. And I tested it recently and got 2 free cruises on one cruise. Uh, so use coding for travel hacking. So, all right, let's get the. Oh, yeah, see, here's loyalty goal met. All right, my projects. I guess I could start a new project actually, because we're going to get into structs now. Okay, so last time we talked quite a bit about pointers, right? And messed around with all the different syntaxes, the asterisk and the ampersand syntax. I had it somewhere in here, right? Yeah, here's the special pointer syntaxes. Now, kind of a word of one warning for because reasonably soon after we cover classes, we're going to be transitioning to Java in here, seeing how little we have to do to get from C++ to Java. But one of the things, just to give you a little bit of foreshadowing, is a lot of textbooks, and this is kind of the reason I don't use a lot of coding textbooks, is I think I know better than they do. Um, is most Java textbooks will claim that pointers don't exist in Java. The reality is that every object in Java is a pointer. So what Java doesn't have is they don't have a special syntax for working with pointers. They don't have this asterisk and this ampersand dealy because Java makes the decision for you. When something makes sense to pass it by address to give you a pointer to where you can find it, Java makes that choice for you. When you should pass something by value, for instance, like an int, Java makes that decision for you as well. But what that translates to is in Java, you cannot pass a primitive type integer as a pointer. You can't pass the address of it. You can get around it by using an object type for integer. There's an integer class in there and accomplish the same thing, but it's in a roundabout way. So just consider last class, all of our examples that we were using for initially learning about pointers were us, let this person in, were us messing with integer pointers, right? Passing ints into functions, showing that when you pass it in, not as a pointer, when you pass it by value. So let me actually give some definition to that. I'm not sure why those are indented, but whatever. So I just want to get a slide up real quick for pass by, let's see, called passing values to functions. Pass by value means we give a copy of the value to the parameter. So any changes made inside the function to that variable are not felt outside of the function. Usually it's called does not have side effect. And then we would, so pass by value effectively means don't use a pointer to pass. Ay, ay, ay. I guess it's not the worst bad word I've written in a text in a slide. We've had some pretty questionable things. Did I ever tell this class? this is years ago, like a decade ago, we were writing like a password generator. And in hindsight, I shouldn't have used four-letter passwords as our example. Very first word randomly generated was the F word. Very first one, just boom. On recording. You can probably go back and find it. It'll be CSC. It might be 200 or 250, one of the two. It used to be called 200 instead of 2000. But it'll be somewhere in my um, playlist or whatever, probably a decade ago. All right, so we're not going to use a pointer to pass the value, which means that we're giving it a copy. If we give it a pointer, we're giving it the address where it can find the real McCoy. Okay, but if we're just giving it an int, we're passing an int a into a function, we're passing it by value. We're passing a copy of that. So any changes we make to that variable inside that function die at the end of that function, as opposed to pass by address. Sometimes this is called pass by reference. Means we pass the address where the variable is stored in memory so that changes made are felt outside of the function. This is said to has side effect. So use pointers. So there's kind of a single slide rationale for when to use pointers versus when not to use pointers. At the very least, if you're using a pointer, somewhere in there you wanted to pass this through the feature in your head that says, or the function in your head that says, am I getting what I want out of this? If I'm going to make changes to this guy inside the function, does pass it, then I should pass it, and I want those changes to be felt outside of the function. I need to pass a pointer. So I'm making modifications to the real deal, to the actual variable. If I want to pass this and I might make changes to it, but I don't want those changes to corrupt what's happening outside of that function, I want to go back to my old value like we looked at in class last time, then I want to not use a pointer. I want to pass it the primitive type, which will give me a copy of that value for use by the function. The other rationale for using pointers is what? Is there a situation where you would choose to use a pointer even if you were not going to change the value inside the function? We talked about this last class. I was probably referencing you inviting me to a party or something like that. Something along the lines of, if you're having a party tonight and you're inviting me to the party, you would never hand me the house, right? And tell me to open the door at 8. You would give me the address where I can find the house. Reason being, houses are heavy, take up lots of space. So sometimes we use pointers when the value that we're passing in is big. So even though we don't have a reason to change it, and we don't intend to change that value inside the function, therefore it doesn't matter whether any changes are felt outside if we're not going to change it. But that allows us to get the value into a function with less effort. Let's say if we try to translate it into real life, you're not having to carry the whole couch into the house. You're just telling them where they can go find it or something along the line. That's maybe a weak example, but now, what if you want to pass something by address? So you want to give a pointer, and you want to make a change to it inside of the function, but you don't want that change to be felt outside the function. So that's kind of a third example, right? So we talked about the first two. I want to pass a small value. I want to make changes. I don't want them to be felt outside, so we pass by value. I want to pass a small value, but any changes I make, I want to be felt outside this function. We're going to choose to pass that small value by address so that we're working with the original value. Third option would be, what if I want to pass a big value, but I want those changes to be felt outside of the function. Well, then we would pass it by address, knowing that any changes you make, you're making to the original. Fourth option is, what if I want to pass in something large and I'm going to make changes to it, but I don't want those changes felt outside the function. That means I'm going to pass it in by address. I'm going to pass it in by a pointer because, by our example, houses are heavy. So it's a big value. So I'm by default going to pass it in by address since it's too big to pass in by value reasonably. But if I internally plan on making changes to that, but I don't want those felt outside the function, most modern languages, actually, I'll ask the question for a couple of you who have some more background in programming. Do modern languages have facilities for solving this? And if so, how? How does a modern language allow you to pass in a pointer to an object, make changes to that object inside of the function, and have those changes not be felt outside of the function? Anybody know? For a majority of the class, I mostly expect you to not even know what I just asked. So most modern languages, if you look at, here, I'll just even show you real quick. So we'll look at Java real quick, because pretty soon here, we're going to be looking at Java documentation. So we're going to look at Java object class. So when we talk about object-oriented programming, one of the things we're going to see here is that all object-oriented languages start off with this top-level generic object called object. They're all built off of this guy. And we actually see it already on the screen. All objects have this function called clone that returns a copy of this object. So you can pass the object in by pointer, giving us the small version of it. So instead of passing the house, you're telling us where to find the house. But then you can call this magical clone function, which is kind of like having a wizard. After you already have the house, he poofs, makes a duplicate of it, and it copies in memory. So what it does is if it's already taking up a megabyte of memory, it'll just create a new megabyte of memory and copy all the contents over to that. And now you're working with a copy of it. So you accomplish the same thing, yet you get it into the function lightweight. All right. Not going to test you over that, just piece of trivia thing out there for those of you with ears to hear. Incorporate a little Bible verse in there. All right, so these things are put into place. So one of the things that's always fascinating when you're learning new languages after you're starting to build up your programming skills. So imagine this last conversation, even if it went over several of your heads, you comprehended it way better than you would have day one of class. You're in the right neighborhood now. So fast forward 6 months or something like that. These are things that you're actually going to be curious about, is how does this language that I'm about to learn handle these special situations, these special cases? And you'll find that when you go and do the hunt through there, you'll find some interesting stuff. And we'll be back to the documentation pretty quickly when we talk about static versus non-static variables and functions. So more information to come soon. All right. Okay. But we could always translate almost everything with programming back to real life examples. In real life, you would never hand somebody the house. You would always hand them the address where the house is, right? Because houses are always heavy, okay? In Java, those decisions are automatically made for you. That's why they don't have a syntax for whether you can pass in things by address or pass in things by value. It just does it. You pass the thing in, we'll figure out how it should have been passed in. And let's call it 99% of the time, probably more than that, it picks right. But every now and then, a programmer, probably a relatively advanced programmer who's probably doing something they know quite a bit about, wants to do something interesting where they're willing to pass in something large to accomplish what they want. A language like Java does not allow them to directly accomplish that. They would have to do it through that clone function. Where C and C++ don't supervise us. If you want to be stupid and you want to hand people houses, you can. Just don't pass it in by pointer. Here's a house. All right. At the end of the day, just like we've talked about earlier in this course, we have a lot of memory in our computers, so most of the time it's not going to be a problem regardless, which is actually kind of the difficulty with programming. And again, why I pick an older language as our first language, because if you never knew that that was a choice, you're not appreciating what Java's trying to do for you. So if you look at even a newer language like C#, which came after Java as a result of a lawsuit, Microsoft tried to steal Java, Sun Microsystems, now Oracle, sued them, lost, Microsoft released C#, which is basically Java. But C# has they've reintroduced the special syntax for pointers. So you can use that inside of C#. And what's interesting is you have to put it inside of a code block called unsafe. You put it inside of an unsafe code block. Not commonly used, but by example, I just said every now and then an advanced programmer might want to do something kind of against the grain. So a language like C# says, look, just throw it inside of an unsafe thing, which is your way of telling us, look, I know what I'm doing. Don't try to intervene. You can accomplish it. Good.
You talked about how the memory and usually it's safe and stuff when we can use like when we what's the word, like we can use more than we need to. When does it not become a problem? Like when do you
Oh, okay. So you're saying where do you make that? Let's assume that we're not doing anything special. And how do you make that decision of when should I use a pointer versus not use a pointer based on how heavy it is? That's kind of what you're asking. So last time we had been talking about kind of the size of a pointer, and that's changed over the years, right? Now we deal with 64-bit operating systems. The majority of our operating systems are 64-bit operating systems. So typically they're going to use 64-bit addresses. We've seen that the addresses we're getting as our output are actually 48-bit addresses. We figured that out by just counting the letters, right? The number of hextets, the hexadecimal digits we see in there, and each one we know is 4 bits big because we can represent the entire hextet 0 through 9, A through F using 4 bits. So we can take the number of letters times 4, that gives us 48 bits. What that's telling us is kind of what's under the curtain for modern operating systems is that most modern operating systems, even though they have a memory manager that's 64 bits compatible, they set aside 16 bits of that specifically for protected memory usable by the operating system alone, which leaves 48 bits for user pointers, us, when we're talking to the operating system, writing our own programs that we would prefer not to overwrite chunks of the operating system in memory. We get 48 bits for our memory addresses. So operating off of that, and that argument would change over the years. We roll back to the 32-bit time, we would have had 24 bits for, let's say, for user space and 8 bits for super user space, whatever. But so we're going to say that today, the average memory address is 48 bits.
That's like the max amount you can use for the memory.
That's so 2 to the 48th power is the number of unique things we can store in memory, okay, regardless of how much RAM you have. We can't count bigger than that with 48 bits. So to the core of your question then is, if I know a memory address is 48 bits, and I know an int is 32 bits, if we're only operating off of size, not whether or not we're going to change the value, we would say, okay, well, it is lighter to pass 32 bits than 48 bits. Therefore, you would pass an int by value, not by address, unless you had a really good reason to pass it by address, like you wanted to make a change that was permanent. Okay, well, now let's move up to a long instead of a int. A long is how big? How many bits is a long? Ints are 32 bits, so longs are 64 bits, okay, or 8 bytes. So which is bigger, 64 or 48? 64. So if you were deciding whether or not, if you were passing along to a function and you were deciding, well, do I pass the 64-bit value? You can almost think of that as weight. It weighs 64 bits. Do I pass the 64-bit value or do I pass a 48-bit value? Well, 48's lighter, right? Okay, but that comes with consequence. So if you're going to pass a pointer to that long, because technically it only weighs 48 bits instead of 64 bits, you've now opened it up where if you make changes to that long inside of your function, those changes will be permanent because you're messing with the original value, not a copy of it. All right. But so let's assume that you really wanted to protect against that. You didn't want to make changes. Well, you could internally inside of your function just create a new variable, which is still using the memory in there to copy it over. Or you can just say, look, the difference between 48 bits and 64 bits isn't actually that big. You know, it's like the difference between carrying in a gallon of milk or a gallon of milk plus a can of soup, something like that. You know, we're not going to get drugged down to the ground in the parking lot of Meijer trying to decide which of those to carry, right? Okay, so the difference in amount of memory you're using is not great. As opposed to if you're passing in the address of a car, which is 48 bits, or an actual car, which I don't know, let's just say it's 10,000 bits. in our example here, cars are pretty heavy, right? At that point, that decision is more meaningful in terms of utilizing memory in a reasonable way, because now the difference between 48 bits and 10,000 bits is significant, right? All right, so just kind of keep that in mind when you're making those decisions. The general approach for a modern programmer is not to worry about wasting memory too much unless it's in an extreme example like that. Okay. We're not losing sleep over 48 bits versus 64 bits. Pass it the way that pass it by value. I would say 95% of the time longs are passed by value. So you're passing it at 64 bits, even if you're not making changes to it, that you're passing it by value just because that's typical convention. But then you have the other extreme where some people just pass everything as addresses for no good reason that makes their code harder to read, which is decent for job security, I suppose. But that's another thing you'll see when you see somebody doing everything as addresses. Well, I suppose they might be on something. You know, you never know what's going on there. Programmers get fairly crazy when they're just watching Netflix and coding, and then they start getting into crazy stuff. But in general, we don't really worry about memory too much anymore. It's not the problem that it was back in the 70s and 80s. All right. So let me give us an example here. Actually, I'll write it in a slide first. So as we continue our voyage through history here of how our languages have evolved and how we have these new tools to solve problems as we bump into them, let's go ahead and create a problem for us that we end up capping out at our current toolbox, stuff we know how to do right now. So we're going to use something simple. So let's say we are working with fractions. Okay, everybody remember fractions? What was that? Third grade? Something like that. Okay. So fractions have two things, right? Numerators and denominators. So we have a numerator. We have a denominator. Numerator is a dude on top. Denominator is a dude on the bottom, right? Okay. So we have a numerator and a denominator. What if we want to represent two fractions and add them? Well, let's say represent two fractions and write a function that takes those two fractions as parameters and returns a fraction that is the sum of those two fractions. All right. Everybody understand kind of what we're trying to accomplish here? So we're trying to say, hey, I want to have like 1/2 plus 1/4. I want to add them together and give myself the sum of them, right? So what 1/4 plus you got to get the common denominator, right? Okay, what do we end up with there? 4/6? What is 1/2 plus 2/4? 8. So we got 4 plus 2, 6/8, right? All right. So, then you can reduce it from there if you want. But in any case, we are we want to represent this in code using only the tools we know how to do now. So let's go back over here. I'm going to go ahead and throw in using namespace standard. That way I don't have to write this syntax. Okay. So for starters, before we even start writing a function, knowing only what we know how to do now, how can we represent a fraction? Keeping in mind that the numerator and denominator can be any number. So it could be a number that's 1 digit long, could be a number that's 7 digits long. So having the tools we have available to us now that we've learned in class, we'd have to use individual variables, right? So we'd have to say something like int f1 num is equal to 1, int f1 denom is equal to 2, int f2 num is equal to, what I say, 1/4, int f2 denom is equal to 4. So in a roundabout way, have we represented the parts of two fractions there? All right. So by this measure, if we wanted to write that function, in order to take in two parameters, two fraction parameters, we would have to take in 4 different inputs, right? So, and ultimately, I'm going to make my return type currently void. That way we don't have to solve that problem yet. We're going to slam into that in a second. All right. So maybe right now we're going to say we're going to add them together and print the result. Okay, let's start with that instead of return the result, because we're going to have challenges returning 2 values when we only can return 1. All right, so we're going to call this guy add fractions. And this one's going to take an int f1 num, int f1 denom, int f2 num, int f2 denom. I just happen to name them the same variable names because they make sense. It describes what we're trying to hold there. So we'll prototype it up there. We'll go ahead and define it after main here. Okay, so now we want to have, initially figure out our common denominator, right? So common denominator will be our 2 denominators multiplied together. So int common denom will be f1 denom times f2 denom. So that'll be our common denominator. Now we need our new f1 numerator. So let's say int new f1 num is equal to f1 num times f2 denom. So we're cross multiplying there to get that. Int new f2 num is equal to f2 num times f1 denom. Make sense? All right. So now we're going to have int new num is equal to new f1 num plus new f2 num. And then we'll put out our answer. Let's just say this. We'll say new num. What did I underscore it? How did I write it? New num. Maybe put a little slash like that. And then we'll say common denom. So this won't be reduced, but it'll be our fraction. So now we can go ahead. Remember, this guy currently returns nothing, and we're just printing out the answer we solved inside. So we'll go ahead and call add fractions, passing it F1 num, F1 denom, F2 num, F2 denom. And we hide this guy here. Go ahead and run that. We get our 6/8. Those two numbers added together. Makes some sense so far? Okay. So just reminding us of third grade math, but throwing a bunch of variables in there, which makes it more confusing for us. But ultimately, if we slow down and walk through that, there's not anything crazy going on there, right? Okay. We're not going to worry about reducing it right now, even though we already have the tool to do it, right? We can do greatest common divisor of 6 and 8, and then divide both of them by the greatest common divisor of it. Poof, you have the value, the thing reduced. Okay. But what if now we wanted to modify this so that well, we can go a couple different routes to this, but let's say I no longer want to just print the answer. I now want to return 6/8. What could I do? Using only the tools we have now. I've passed in my fraction with 4 separate inputs, right? First numerator, first denominator, second numerator, second denominator. Took 4 different inputs, 4 different parameters to get that information in. I've now added it together. I haven't told you anything about the format it needs to be in when it comes out, other than we need to return the information related to our fraction. So knowing only what you know now, what could we do to accomplish this? What we're trying to do right now is we're trying to reenact history, where we're programmers trying to solve problems. We start bumping into little inconveniences here and there that we may or may not have little workarounds for, but we start seeing the, hey, I wish the language could do this. I wish the language could do this. And then we'll introduce how the language accomplishes that. So anybody have an idea of only what we know right now, how we could return that fraction so that up here, we can say answer equals, keep in mind, I'm not, here, for the type, I'll put a little question mark. Type question mark, whatever that guy's going to be. And then I want to be able to do cout answer and L. And I want to see the 6/8 there. Any ideas? What could I return here? Go ahead. Yeah, we could build a string and then create our fraction as a string. So we could come up here, we can say, okay, well, I'm gonna have a string here. So it's gonna return a string here. So now I know I have my 2 pieces right here. I'll go ahead and comment out this line so we won't actually output. We got an announcement?
Yep.
All right.
Event, we are going to be playing with Arduino boards, so you can actually put your C skills you learned in this class to good use. So I think it's 4 to 7. I can't remember.
Yeah, an Arduino is a programmable control board. So it looks like a piece of hardware, and it has a bunch of pins in it and stuff like that can put, depending on which pin you turn the power on, you can control different devices and stuff like that. But it has a programming language associated with it that just happens to be C and C++. So you already have the background for it. And so you can write your code, upload it to the board. Now the board is a piece of hardware that does your bidding. Kind of a fun thing. I would encourage you. What time is that on Monday, you said?
Yeah, Monday night it's like 4 to 7, 4 to 8.
Okay, 4 to 7 p.m. across the hall there. So it's going to be over CS Lab across the hall. So I encourage everybody to go and take advantage of that. These are cool opportunities you have. Also, CS Club can help you, with problems you run into your homework assignments, studying for midterms, but studying for the final. For those you have to do a lot better on the final, and things like that. And these are 2 of our CS scholars. So these are, both of them are seniors and getting ready to graduate with a master's and a bachelor's in computer science. in 4 years, so they don't suck. Well, a little bit.
Usually.
A little bit. All right. Yep, later. Okay, so he suggested we might want to use a string. So we now have the return type as string, return type as string. We're going to go ahead and have to build our string here. So we'll say something like string answer. We'll start it off as the empty string because we want to build it onto that. So the first thing we want to do is we want to put new num onto this guy, right? Now I think we've seen that you can't just, in Java, I could have said answer is equal to answer concatenated with new num. Java would allow that. It would allow me to take a string and tack an int onto the end of it. In C++, what do we have to do to new num, which is an int? Go ahead. ToString. There are a couple other functions where you can turn it into a char or something like that. But we don't know how many digits long it is. So ToString's probably our way to go. So we'll do, I think it's ToString like that, right? So we'll concatenate on ToString of that. We'll concatenate onto that, a slash. We'll concatenate onto that, ToString of what I call it, common denom. And then we'll return answer. So we just built our fraction out of a string. I guess technically, since we built it this way, we could have just said string answer equals that. We didn't have to concatenate it onto the empty string if we didn't want to. So answer is going to be equal to the string version of new num, concatenated with a slash, concatenated with the string version of common denom. Then we'll return that. That will come firing out of here. Our question mark type will now be a string. And we'll print that out. Same type as standard. Where's 11? What do I have to include string? It's string, isn't it? Oh, hold on. I think it's in standard namespace. There we go. I had my using namespace after this. So as I had it, I would have had to say that to specify it. But now I just used using namespace before it. So that would fix it for me. All right, so there's our 6/8. Well, now what if I need to get the 6 and the 8 out of there? I want to pull it back out into my numerator and denominator. Well, we could write a function that goes through and builds up the numerator until we hit a space. Then we'll skip through the space and the slash and the space, and we'll build up our denominator. Now we have our two pieces that we can then convert to ints, and we can potentially do stuff with them, right? We could pull this off. We had to, but it's starting to feel a little inconvenient. All right. So what else could we do? We need to look at some other tools that these languages have built in for us that allow us to accomplish tasks like this. So in order, the way we're going to hit this is we're going to introduce arrays, then we're going to introduce structs, then we're going to introduce classes. So slight upgrade to better upgrade with its own inconveniences, and then classes, which kind of solve our world for us. Go ahead. Potentially. So what he's saying is we could perhaps go ahead and say, well, I'm going to pass in a pointer to F1 num and a pointer to F1 denom or something like that. That way we have the ability to change it. And then when all is said and done, we can do star F1 num equals our new numerator, and star F1 denom equals our new denominator. And then we would just have to remember that outside of this, then F1 has been modified to hold our values. So if we want to see that version of it, that's pretty clunky, but technically allowed. So now we would say, okay, well, this guy's going to take in a int pointer F1, int pointer F2 or F1 num. So we're basically saying I want my F1 fraction to be changeable, is what I'm saying there. And this is actually a good example because it allows us to show changeable and unchangeable in the same things, even though we could make all of them changeable and just choose to only change F1. But in any case, so what I'm going to do here is, let me just steal these parameter lists here. So now what I can say is, so this is well, first of all, let's pass the values. So add fractions is now expecting F1 numerator and F1 denominator as pointers. How do I modify this to send in the address of F1 numerator and the address of F1 denominator? Ampersand. So we'll go ahead and throw an ampersand here and an ampersand here. I'm not giving you the values. I'm not passing it by value anymore. Now I'm passing it by address. Make sense? So then inside here, whenever I use F1 denom, I have to say star F1 denom. Because otherwise F1 denom in here is an address, not a value. Star F1 denom is the value that lives at that address. Whenever we use F2, we're not doing anything special because we just passed F2 in by value. Star F1 num. Star F1 denom. All right, so now we have our new numerator. And what we can do here at the end, before we create our string answer, is we can say star F1 num is equal to our new numerator. Star F1 denom is equal to our common denominator. We would then change the return type to void. This guy would do its thing. And then what we would do afterwards is we would print out F1 num followed by a slash followed by F1 denom. And we get our 6/8. Let's walk through that for a second. All right. So when I I initially defined everything as just ints. I wrote my function and I happened to pass in the first two parameters, basically my first fraction, F1. I passed it in by address and made it changeable so that it could be felt back out here in main. Inside here, I did all the same math, but anytime I used F1, I had to make sure I dereferenced the pointer to get the value. That's where I put that star in front of it. Whenever I used F2, I didn't have to do anything special because F2 was just a plain Jane int. So I did all the same math as I did before, but then when all was said and done, I updated the value that lives at this memory address to this new numerator, and the value that lives at this memory address to this new denominator, so that when this function ends, notice I didn't return anything here. When that function ends and I'm back out here, when I output, so just to give you an idea here, I'll print out the fraction beforehand and afterwards. F1 num, F1 denom is 1/2 before I call that function, right? So just so we see it, there's my 1/2, then I call the function, and now it's magically been changed to 6/8. So it's 1/2 before I call the function. I call the function, passing it my F1 stuff by pointer, by address. And then I make sure I modify those two variables inside there. So when I'm done, when I bounce back out here to main and I start working with F1 stuff again, it's now been modified. All right, that makes some sense. Clever approach, but we're starting to see how this is, we're getting a little janky here, right? This is a little bit hard to follow. You might want to put some comments in here, what you're trying to do. Somebody looks at your code here and says, why are you only passing half the crap in as pointers? we could have put on a good show and passed all 4 parameters and pointers and just happened to take advantage of their pointerness as for the F1 guy, things like that. But at the end of the day, you accomplished it, right? This is kind of like fixing stuff around the house with duct tape and a screwdriver. Right now you're carrying around a toolbox with just the crap I've taught you in class, right? And even though some of you have more stuff in your toolbox, if you had programming and stuff before, it's still interesting to try to solve problems using a limited, with one hand tied behind your back, right? So, and I promise you it builds your programming skills. Yeah, so in any case, these are fun little things to do. But if you put yourself in the shoes of a programmer from years and years and years ago, when you start feeling like to do something that feels reasonably simple, adding a couple of fractions together, 3rd-grade math, and you feel like you're having to hack the planet in order to make it work, you start feeling like, okay, maybe this programming language could use a couple of upgrades, some features, right? All right. So any questions about what we just did here? In fact, for right now, I'm actually going to save. Oh, I didn't do, let's call this guy pointer practice or whatever. Whatever. And I'll share it. So for those of you who are interested in just this exact example, I'll go ahead and pointer fraction example. I'll just throw that in Slack if you want to go and study that later. Any changes I make now will be in a new link, so that'll be solidified forever. You'll have access to this code. So any questions about this at this point? Okay. You're doing an excellent job about possibly avoiding the homework over the weekend, by the way. You're unnaturally delaying me, but these were good questions. But we'll see. Let's see if we can play catch up. All right. So now we saw the problems representing fractions as 4-ints caused difficulties in pulling this off. So in steps in something called an array. I know some of you have already run into arrays as you were scrambling to try to solve the midterm practice stuff, not using just the tools you've learned in class. So you started looking at options that you found on websites or whatever. So you got a little bit of a precursor to this guy. So right off the bat, what you can do is we can say arrays are kind of like strings. Decent starting point. That is, they are 0 indexed. They hold a collection of like type values. So really a string is a collection of chars. That's what makes up a string, a whole bunch of chars. In fact, remember I've told you when we first introduced strings in here, I introduced the 2.5 times evolved string. So the current strings we're using in C++ are not original C++ strings. You would hate original C++ strings because they operate like arrays. So you're about to hate these, which makes it fun. But the real reason is arrays actually aren't really a problem. It's because of the nature how we use strings. It's very convenient for programmers to have kind of powerful tools around strings to conveniently work with them. And if we don't have the ability to like quickly concatenate and things like that, strings become difficult to work with. Old school day one strings were represented as character arrays, which are pointed to by char pointers. We'll talk about that. All right. But effectively, when you first think about arrays, you want to think about they're kind of like strings. Strings are collections of specifically chars, where arrays are collections of like type values. we have a single variable name attached to, let's call it many individual values. Just like when we say string S equals hello world, we have a single variable named S that in some potentially meaningless way represents this collection of chars that spells out hello world. Make sense? So what arrays do is they allow us to expand this idea of storing a collection of like type values under a single variable name away from just chars to now we can do it with things like maybe ints. Maybe an integer array that has two buckets. Bucket 0 is the numerator. Bucket 1 is the denominator. Something like that. All right, so let's go and look at this. So I'm going to write, we're going to write multiple versions of the same function. So here we'll leave our creepy one there for now, because I mean, really, it's actually a pretty good one. It just, it's a hack to get that to work, that one, right? So we're going to go ahead and say, let's start off with the return type. So we're going to return here an int pointer. You'll see me fill in the gaps here in a second. And we're going to call this guy add fractions. It's called add fractions array, just to kind of label this. And this guy's going to take an int pointer fraction 1. Actually, I want to, here, let me, well, we're going to do it this way. And an int pointer fraction 2. All right. So for right now, let me just comment this out for a minute, because we're going to come back and write it here in a few minutes, but let's introduce this idea of an integer array. So we're going to start off with what I'll call, let's just call them bad arrays, but it doesn't necessarily mean unusable arrays. But one rule of thumb you might run into in programming is a lot of times when there is multiple ways of accomplishing something, the way that seems the simplest to work with might often be good enough, but probably comes with some caveat that makes it break sometimes. We're going to see that here. We're going to look at the easy way to define an integer array, and then let's call it the ultimate flexible integer array, and see the difference between those two. But let's start off with a convenient one. So we're going to say we're going to have an int array. We'll call this guy f1, and it's going to hold 2 values here. We're then going to have an int f2. It's going to hold 2 values. We'll say f1 at bucket 0 is going to hold a 1. f1 at bucket 1 is going to hold a 2. f2 at bucket 0 is going to hold a 1. f2 at bucket 1 is going to hold a 4. So now we've stored our 1/2 and our 1/4, the components of that, into 2 variables instead of 4. Even though those 2 variables each internally encapsulates 2 variables. So we still have 4 values stored. We're just doing it by way of 2 variables initially. All right. So what if I want to write a loop that goes through every element of f1 and displays the contents of it? So think about this like a string. We're going to write our common string syntax here, and we're immediately going to slam into a wall. So we're going to say int I is equal to 0. Now, if we were dealing with a string, we would have said f1 dot length, like that. If we were working in Java or C#, we would say f1 dot length, like that. Not a parameter, or not a function. Instead, it's something called a field. It's a variable associated with the array class. That'll make more sense later. So we'll say I is less than that guy. None of these work in C++ when dealing with arrays. Arrays in C++ don't know their own length. We've actually seen this before. If you remember way back, kind of the maybe week 2 of class or maybe the end of week 1 when we first looked at C++ code, we see it's conveniently omitted here. But remember when we talked about command line arguments? And in C++, this was in the same conversation we talked about all programs beginning and end with main. If we wanted to pass things in from the command line when we run our program, if we want to say cat, dog, elephant, along with the, running the program after compiling it, we would need to have some parameters come into main. And the common parameters for main in C++ would be int argc, and then char pointer argv. Here, I'm going to write it in a way that scares you less. There we go. We'll scare you more later. So char pointer argv array, which is a char pointer. I know we're just newly introduced to the single asterisk, so let's not freak ourselves out with the double asterisk yet, even though you already know what it means. Trust me. All right. So we see the evidence of my statement right here. Arrays in C++ don't know their length. Well, here's an array being passed in that's going to hold the values of our arguments. That's why typically that variable is called argv, argument values, command line arguments. Like if we were running this program, and typically when you compile a C++ program at the command line, it is usually a program called a.out that it generates. So if we wanted to say cat, dog, elephant, when we were running this program, executing it, this is if you were actually executing it for the command line, not just hitting the magical run button. All right. So if we were running this from the command line and we wanted to get these 3 values, for example, into our program, those 3 values would come in to argv here. So argv at bucket 0 in this case would be a.out. Argv at bucket 1 would be cat. Argv at bucket 2 would be dog. Argv at bucket 3 would be elephant. Argc would be 4. That is, there are 4 values coming in. The name of the program and all the command line arguments, the 3 command line arguments. Newer languages don't take in the name of the program. So in Java, argc would be, if argc existed in Java, argc would be 3. The Java version of this thing here is public static void main string array args. So this is what main looks like for Java. A string array inside of Java knows its own length. So we can say args.length, and that would give us, in this particular case, it would give us 3. So if we were running this program in Java, we would say Java, what's the name of actually this program is called main. We'll talk about that later. And then we would say cat, whatever, those things. All right. And those 3 parameters would come in, and this string array would have 3 elements in it. But Java's arrays and C#'s arrays can report their length themselves. Arrays in C++ cannot. That's why we needed 2 parameters here in main to accomplish the same thing that 1 parameter did in main in a newer language. All right, makes some sense. Now, command line arguments are not necessarily common today, especially among business programmers when you're writing a lot of graphical user interface stuff. But it's still quite common if you're a back-end developer doing stuff on servers and things like that. Then you might take in command line arguments all the time, or you might read in a file, things like that. All right, so we dump that. Typically, since we don't use command line arguments, we typically will leave that empty. Java actually doesn't allow you to leave it empty. You gotta prepare for command line arguments even if you never use them. So it's a, I don't know, it's a thing. Java has a lot of stupid things. It's a lot of good things, but then you see they overstepped a couple times. All right. So f1.length here. So again, we created two integer arrays up here that just happen to each be able to hold two elements. I filled each of those two elements up with the components of my arrays. So I have two variable names, f1 and f2, that can hold the components of my arrays. But when I get into my for loop here, we're trying to write it like we would for strings. We immediately hit a snag in that arrays in C++ cannot report their length. So for right now, I'll just hard code in a 2. Somewhere I'm going to have to store how many elements were in there. You know, maybe I did something like int fraction size is equal to 2. And then when I built my fractions, I built them in terms of fraction size, something like that. Then I can say I is less than fraction size. So if I ever change fraction size, it would loop more times. I could do something like that to keep track of it. But this is just a variable that ultimately holds the number 2 right now. I plus plus. Ninja. And then inside here, we'll do cout f1 at bucket I. All right, we go and run this. Oh, sorry, I still have my example down here. Get that dude out of there. There's my 1 and my 2. Those are the components stored of my fractions stored in bucket 0 and bucket 1 of f1. If we were to change f1 to f2, we'll get the 1/4. But we had to know the length of those fractions. All right. So now if we wanted to write our add fractions array, passing it these fractions, we would call add fractions array. I'm sorry, yeah, add fractions array. This guy takes in 2 int pointers as parameters. I would pass in f1 and f2. Now, before I do that, let me just show you something. This is the value of f1. This is the value of f2. So when I created my fractions here, they are already pointers. F1 holds a memory address. Now, just to connect you back to something we've done previously, let's see, where's my picture for strings? Remember this dude? So a string is indexed from bucket 0 up to its length minus 1, but those things are actually in memory somewhere. And notice that these chars live in memory right next to each other. Make sense? So if I steal this slide, just to show this for an int array, int array storage, and I say something like int f1, just so I can keep my picture right. So let's have it hold 4 things. All right. And if we operate off the same example, let's just say, to keep our memory addresses simple, it handed me memory address 100 instead of this big hexadecimal value. 100's friendlier for us, right? So we're just going to say when I asked the operating system for to create this array for me, it gave me memory address 100. So if I were to print out the value of F1 in this case, I would get 100 printed to the screen. But since I'm holding integers here, let's just say this holds 1, 2, 7, 9, whatever. Okay, so since this holds integers, and keep in mind that it's still a 0 index. So this is bucket, the first bucket is 0 up to its length minus 1, whatever its length is, because it can't report its own length. Some of you have submitted some assignments or had answers on your exams that were obviously using some either external sources, or you already knew something and used some tools from that you already knew that we haven't introduced in class. Can anybody tell me what is likely the upgrade to integer arrays in C++ if you want it to be able to report its length? So the equivalent of an integer array in Java in C++, one of the main things to accomplish that is something called a vector. Vectors can do it because they can hold a collection of values, but they can also tell you their length. Okay, but we're purposely not using vectors here because I don't like you. Pointers are fun, right? We want to mess with pointers. It gives you an understanding of what's happening under the hood. And once you really understand this stuff, all the other crap is so much easier. Because you're like saying, man, this is automatic transmission. I'm basically in a Tesla. It's driving itself. Hands are off the wheel. But you want to appreciate what it's doing for you first. All right, so an integer array will give us a memory address. And in this case, since I created the ability to hold 4 integer arrays. How big is an int again? 32 bits, 4 bytes. So that means I need 16 bytes of memory in order to hold 4 integers. So let me get rid of that. So we need 16 bytes or 128 bits of memory to hold the array. And I'm going to throw a word in here. I think I've mentioned it. Contiguous memory to hold the array. What does contiguous mean? We're showing an example of it right here. What does it mean for memory to be contiguous? Right next to each other. All right, because that's how this thing down here worked. We'll rewrite this here in a few minutes, but in very few minutes because we're almost out of time. All right, so we need, so instead of it being 100, 1 byte over, in a string we were holding chars. Now we need to move 4 bytes over. So this is going to be 104. Because 100, 101, 102, and 103 held the 4 bytes of our first int. 108, 112. Same syntax. If we were to build a char array that held 4 things, it would be 100, 101, 102, 103. This is creating enough memory to hold this many of those guys. Make some sense? All right. Now, let me just drop back down to our code here. So there's our 2 fractions. We saw that they're already pointers. When we call add fractions, we'll pass in those 2 values. Add fractions array is expecting a pointer and a pointer, 2 integer pointers. Am I handing it 2 integer pointers here? Is F1 a pointer? I highlighted its value right down there. That dude look like a pointer? Looks like a memory address? Does this dude look like a memory address? So F1 and F2 are already pointers. It would not be correct for me to say ampersand F1. That would show me the address where the variable named F1 actually lives, not the value that it holds, but the variable itself where it lives. All right, so F1 and F2 is how I should pass this in. So for homework, add these fractions together and display, actually, and return the result. Okay, so this is going to be your homework assignment. I'll give you this code as a starting point, but I'm going to say something out loud here as a little word of warning. Make sure that you create a new fraction in here. Actually, you don't even need a new fraction, but ultimately make sure you're returning this fraction. Next time we're going to look at, what if I wanted to write this and I just wanted to update fraction 1 to hold the contents of my answer? Kind of like our version of this guy down here. That actually won't work the way we have it written right now. I mentioned a few minutes ago that usually when you have an easy way of defining things, there's usually a caveat. The punchline to that, which we'll talk about in a lot more detail next class, is since we use the shorthand syntax for defining these variables, these memory addresses are protected and only directly changeable in main. So when we come back to main, those memory addresses will not be available to us. And what you're actually going to see is when you get into your code here, these, you know what, actually, I can't even give you this yet. I can't give this to you yet. Because what's going to happen is when you come into here, you're going to see fraction 1 and fraction 2 are filled up with zeros. Because the memory addresses are not accessible from in here, even though you passed in memory addresses. All right, so I guess no homework over the weekend. But man, I'm gonna make Tuesday's assignment just impossible. Oh my gosh. All right, so take a breather after your midterms. This was not my intent. It's a couple of your faults. But we'll come back on Monday and I'll fill you in on what I just said, how these memory addresses don't pass in right. And I'll show you the alternative way of creating arrays, which probably should be the way you always create arrays so you never run into this problem. All right, questions, comments, concerns, bribes? Go ahead.
Said not Monday. That's when we have class.
Yeah, didn't I say Tuesday's homework will be impossible? Or did I say Monday out loud at some point too?
Yes.
I get so excited with programming. I'll see you on Tuesday. All right. Everybody have a good weekend. Enjoy your reprieve from the
The assignment after this one's supposed to be the difficult one.
Yeah.
I guess you were.
Oh yeah, that was gonna be crazy. Yeah, you guys should all drop now. All right. 1 second. There is stuff.